You've probably held two magnets near each other and felt that invisible push or pull. It doesn't make sense. There's nothing there. No strings, no air pressure, no contact, just emptiness between your hands and a force you can feel but can't see. And if you've ever asked someone to explain it, you've probably heard something like opposite poles attract or magnetic fields. But that's not an explanation. That's just renaming the mystery. Today, we're going to do something different. We're going to understand magnets the way Richard Feynman thought about them, not by memorizing facts, but by recognizing what's actually happening when reality refuses to let two objects ignore each other. Here's the promise. By the end of this, you'll see magnetism not as some weird exception to normal physics, but as a consequence of something deeper, something that connects relativity, electricity, and the structure of reality itself. And the strangest part, the force you feel when you hold those magnets isn't even a fundamental force at all. Let's start with what magnets actually do. You bring two bar magnets close together, North Pole, near North Pole, and they push apart. Flip one around so North meets South, and they snap together. We've all done this. And here's the first misconception people carry around. They think magnetism is its own separate thing, unrelated to electricity. That's wrong. Magnetism and electricity are the same phenomenon, just viewed from different perspectives. But that sounds like physicist nonsense, so let's build it from the ground up. Imagine a wire, copper wire, perfectly straight, sitting on a table. Inside that wire are electrons, trillions of them drifting slowly through the metal lattice. And I mean slowly. When you flip a light switch, the electrons themselves move at about 1 millimeter per second. Glacial. But the electromagnetic signal moves at nearly the speed of light. That's the first thing people get wrong about electricity. The electrons don't race through the wire, they shuffle. The energy moves fast, but the charges themselves crawl. Now picture this. You're standing still next to that wire, watching those electrons drift past. You see negative charges moving in one direction. Positive charges, the atomic nuclei in the copper, are fixed in place, locked into the lattice. From your perspective, there's a net flow of negative charge. That's an electric current. And here's where it gets strange. That current creates a magnetic field around the wire. You can prove this with a compass. Bring a compass needle close to a current-carrying wire, and the needle deflects. The wire isn't magnetic in the sense that a bar magnet, but it's doing something to the space around it. Pause and predict what happens next. If you start moving alongside the wire at the exact same speed as the drifting electrons, what do you see? Think about it for a moment. Here's what happens. If you move with the electrons, they look stationary to you. You're traveling alongside them, so from your perspective there's no current, no moving charges, just a wire full of static electrons and static positive nuclei. And here's the twist. From your perspective, the magnetic field disappears. But you still feel a force if you're holding a charged particle nearby. That force didn't vanish. It just changed identity. What you saw as a magnetic force when you were standing still is now an electric force in your moving frame. The force is the same. The label changes. This is not a metaphor. This is relativity. Not the dramatic time dilation, black hole kind of relativity, but the everyday kind that governs how electric and magnetic fields transform when you change your velocity. Magnetism is what electricity looks like when you're moving relative to the charges. They're two sides of the same thing. Physicists call it electromagnetism for exactly this reason. It's one unified field that splits into electric and magnetic components depending on your motion. Let's make this concrete. You've probably heard that moving charges create magnetic fields. That's true. But here's the deeper truth. Stationary charges create electric fields. And if you start moving past those charges, you'll measure a magnetic field even though nothing about the charges themselves changed. The field didn't appear out of nowhere. It was always there, woven into the structure of space-time. You just rotated your perspective and saw a different slice of it. This is a simplified explanation to make the core idea intuitive, but it captures the essence. Magnetism isn't a separate force. It's electricity plus relativity. And that's why a current-carrying wire generates a magnetic field. The drifting electrons are in motion. From the perspective of a stationary observer, that motion produces a magnetic field that wraps around the wire in concentric circles. Bring another wire nearby with current flowing in the same direction, and the two wires attract opposite currents, and they repel. This is how electromagnets. This is how MRI machine. This is how the entire grid of our electrical infrastructure operate. But now we need to ask the harder question. If magnetism is just electricity from a moving perspective, what's happening inside a permanent magnet? A bar magnet just sitting on your desk, not moving, not connected to any current. Where's the motion? The answer is smaller than you think. Electrons, not drifting through a wire this time, but spinning. And here's the second major misconception people carry. They picture electrons as little balls rotating in space. That's not quite right. Electrons have a property called spin, but it's not literal rotation. It's an intrinsic form of angular momentum, a quantum mechanical property that doesn't have a perfect analogy in everyday experience. But, and this is the critical part, that spin behaves like a tiny loop of electric current, and a loop of current generates a magnetic field. In most materials, the electrons are paired up in atoms with their spins pointing in opposite direction. The magnetic fields cancel out. No net magnetism, but in certain materials, iron, cobalt, nickel, the electron spins can align. When billions of atoms organize their spins in the same direction, you get a magnetic domain. And when those domains align across a macroscopic chunk of material, you get a permanent magnet. The motion generating the magnetic field is quantum spin, intrinsic, always there. Here's the third misconception. People think magnetic fields are something magnets create and shoot out into space. That's not quite it. Fields aren't objects. They're not made of stuff. A magnetic field is a mathematical description of how a charged particle will be influenced at every point in space. It's a map of potential forces. When you hold two magnets near each other and feel them pull or push, you're not feeling the magnets reaching out and grabbing each other. You're feeling the influence of one magnet's field on the other magnet's moving charges, the spinning electrons. The field is the mediator. It doesn't do anything on its own. It describes what will happen if a charge shows up. And here's where Feynman-style thinking becomes essential. Feynman was famous for refusing to accept surface-level explanations. In one of his lectures, someone asked him to explain why magnets attract and repel. His answer was unsettling. He said, "You can't explain it in terms of anything more familiar, because magnetism is already one of the basic ingredients of reality. You can describe how it works, how fields transform, how forces scale with distance. But you can't reduce it to something simpler without invoking the structure of electromagnetism itself, which is fundamental. But we can do better than just saying it's fundamental. We can explain why the force has the structure it does. Let's talk about limits. Reality is built from constraints. The speed of light is a limit. You can't go faster. The uncertainty principle is a limit. You can't know position and momentum with infinite precision. And electromagnetism is governed by limits too. One of those limits is this. Electric charge is conserved. You can't create or destroy it. Another limit, the electromagnetic field carries information at the speed of light, no faster. These constraints force the field to have a specific mathematical structure, and that structure determines how magnets interact. Here's a real-world anchor. GPS satellites. They orbit Earth at high speed, and their clocks tick slightly differently than clocks on the ground. Not because the satellites are magical, but because relativity is real. Time dilation and length contraction are measurable. And those same relativistic effects that mess with GPS timing are exactly what turn electric fields into magnetic fields when charges move. The magnetism you feel from a bar magnet is a relativistic effect, just incredibly subtle, because everyday speeds are so slow compared to light. Let's go back to those two magnets in your hands. North pole near North pole. They repel. Why? Inside each magnet, you have aligned electron spins generating tiny magnetic fields. Those fields extend into the space around the magnet. When you bring two north poles together, the fields interact. The field lines, the imaginary curves that map out the field's direction and strength, oppose each other. The fields don't want to overlap that. It costs energy. The system naturally pushes the magnets apart to minimize that energy. Flip one magnet around. Now north meets south. The field lines from one magnet flow smoothly into the other. The fields align. The energy is lower when the magnets are together than when they're apart, so they pull toward each other. This isn't mysterious once you understand that fields are real, that they carry energy, and that physical systems naturally move toward lower energy states. The force you feel is the system trying to minimize field energy. But here's the fourth misconception, and it's a big one. People think magnetic force is mysterious because it acts at a distance. How does one magnet know the other is there? It doesn't. Magnets don't know anything. The field is already there, filling all of space. When you move a magnet into a region of space, you're moving it into a region where the field has a certain structure. The force isn't magically reaching across empty space. It's a local interaction between the magnet's moving charges and the field present right there at that location. Here's the fifth misconception. People think magnetic fields are permanent, unchanging things, but they're not. If you heat a magnet past a certain temperature called the Curie temperature, the atomic vibrations become strong enough to randomize the electron spins. The domains lose their alignment. The magnet stops being magnetic. Cool it back down in the presence of an external magnetic field, and you can remagnetize. The field isn't an intrinsic property of the material. It's an organized state that can be created or destroyed depending on conditions. And here's the sixth misconception, one that touches on something deeper. People assume magnetic monopoles must exist. If you have a north pole, you should be able to isolate it, right? Just cut the magnet in half, separate north from south. But when you cut a bar magnet, you don't get a north piece and a south piece. You get two smaller magnets, each with its own north and south pole. Cut again, same result. Keep going down to individual atoms, still dipoles. Magnetic field lines always form closed loops. There's no such thing as an isolated magnetic charge as far as we've ever observed. Why not? Nobody knows for sure. Some theories predict monopoles should exist, and physicists have looked for them. They haven't found any. It's one of the genuine open questions in physics. And this is important. Science doesn't have all the answers. What it has is a framework that works astonishingly well within certain limits, and the honesty to admit when something is still uncertain. Pause and predict again. If you take a wire, form it into a loop, and run a current through it, what do you get? Think about the shape of the magnetic field. You get a dipole. The loop of current generates a magnetic field that looks exactly like the field from a bar magnet. One side of the loop acts like a north pole, the other like a south. This is not a coincidence. This is the deep connection. A bar magnet is just trillions of atomic current loops, electron spins aligned in the same direction. Scale it up, and you get the macroscopic field. Scale it down, and you see that magnetism is always at its root, about moving charge. Let's anchor this with another real-world example. Particle accelerators. At CERN, they use enormous electromagnets to steer charged particles around a ring 27 kilometers in circumference. Those magnets are just coils of wire carrying huge currents, generating fields strong enough to bend particles traveling at 99.9999% the speed of light. The force those particles feel is the same magnetic force you feel when you hold two fridge magnets together, just scaled up. The physics is identical. And here's where the limits come back. The strength of the magnetic force depends on velocity. A charged particle at rest in a magnetic field feels no force. Start it moving, and the field exerts a force perpendicular to both the velocity and the field direction. The faster the particle moves, the stronger the force. But there's a limit. The force can only deflect the particle's path, never speed it up or slow it down. Magnetic forces do no work. They can't change kinetic energy. This is a fundamental constraint built into the mathematics of the field. Why does this matter? Because it tells you something profound about the structure of reality. Forces aren't arbitrary. They have specific properties determined by symmetries and conservation laws. The fact that magnetic forces are always perpendicular to motion is a consequence of how the electromagnetic field transforms under rotations and boosts. The same symmetries that give you electric charge conservation also give you the structure of the magnetic force. Everything connects. Here's another reality check. Muons. These are particles like heavy electrons, and they're constantly raining down on Earth from cosmic ray collisions in the upper atmosphere. They're unstable. They decay in about 2 microseconds. At the speeds they're traveling, they shouldn't make it to the ground before decaying. But they do. Why? Time dilation. From the muon's perspective, the journey is shorter because of length contraction. From our perspective, the muon's clock runs slow because of time dilation. Either way, relativity is real, and the same relativistic framework that explains muons is the framework that unifies electricity and magnetism. So here's what we've built. Magnetism isn't a separate force. It's a relativistic side effect of the electromagnetic field. Permanent magnets work because of aligned quantum spins, generating tiny current loops. The force you feel is the interaction between one magnet's field and another magnet's moving charges. Fields aren't mystical. They're mathematical descriptions of how reality distributes forces across space, and the whole structure is governed by limits: the speed of light, charge conservation, the impossibility of isolated magnetic poles. Which brings us to the final question. If magnetism is just electricity plus relativity, why does it feel impossible? Why does it feel like magic? Because your brain evolved to understand contact forces. Push a rock, it moves. Pull a rope, it follows. Those are intuitive. But fields aren't objects you can touch. They're abstract. Your senses don't directly perceive them. You only feel their effects. When you hold 2 magnets and they push apart with no visible connection, your intuition screams that something is missing. But nothing. The field is there. It's real. It carries energy and momentum. It can be measured. You just can't see it with your eyes. And that's the deeper lesson here. Reality doesn't care about your intuition. It operates according to rules that are often completely alien to everyday experience. Quantum mechanics is like this. Relativity is like this. Electromagnetism is like this. The universe is far stranger than it appears on the surface. But it's not arbitrary. It's structured. And once you learn the structure, the magic doesn't disappear. It just shifts. You stop being confused by magnets and start being awed by the fact that space-time itself is woven from electric and magnetic fields that transform into each other depending on how you move. Feynman's approach was always to dig below the labels and ask what's really happening. Not magnets attract because of magnetic fields, but what is a magnetic field? Not opposite poles attract, but why do they attract? The answers take you into relativity, quantum mechanics, and the fundamental structure of forces, and the payoff is worth it. You gain a way of seeing the world that reveals connections most people never notice. So the next time you hold 2 magnets and feel that invisible push or pull, remember you're feeling the limits of reality itself, encoded in the electromagnetic field, mediated by relativistic transformations of moving charge, and constrained by the deepest symmetries we've ever discovered. Magnetism isn't impossible, it's just reality refusing to be simpler than it actually is.